started with the webinar, and today's presenter is Karen Greenhouse, who is the Director of Professional Development here at Key Curriculum Press, and she's going to talk to you about various models for presenting solving equations in algebra. And looks like Karen's just about ready to get started.
I am. I'm trying to pull up. Ooh, there it is. So hopefully everyone should be able to see my sketch. Can you see it, Andres? It looks like everyone. Okay.
Looks like we're ready to go. So
okay.
Take it away, Karen.
So as I was saying, one of the ways to participate is by asking questions in the question panel, and Andres and Scott will be answering those for you. But I'm also going to be sending out polls periodically. So I wanted to start with a poll, since this entire presentation is on how to solve equations in different ways that you could help your students visualize solving equations. I wanted to just get a feel for what you all are doing right now with your students. So I'm going to send out a poll, and I apologize for my Mac users, but apparently the polls get cut off. So I'm going to read the question as well. And you're going to see a poll, and it's very easy to answer. You simply choose your answer and hit submit, and it gets sent back. So here is the first poll, and I will read the question for my Mac users who might have the question being cut off. And the question is, what methods of solving equations do you use with your students? So in this particular one, I believe you can choose more than one possible answer, so I'll give everyone a couple minutes to respond, and then we will shut the poll down and get started. And I got about a little bit more than half of you right now. So we got a good mix of things going on. Looks like a lot of you are using all three choices up there, lots of different options, which is great for your students that you use more than just one. Okay, it looks like most of you have voted. I apologize if you didn't get to vote, but I'm going to close so that we can move on, and I'll just share the results. So it looks like we have a good diversity. Everyone is doing different things to help their students understand solving equations, and that's what we're going to do today in today's presentation. And so on the screen right now, I just wanted to kind of briefly go through the 4 ideas that I'm going to focus on in the presentation, just to give you an idea of where we're going. So we're going to start with, if my, it looks like my sketch has frozen.
You need to choose the arrow tool.
Oh, thanks, Andres. Thank goodness I'm not a beginner Sketchpad user. All right, so here we go. All right, so we're going to start with solving equations by undoing, and then we're going to move into using a visual way to solve equations by approximating solutions. So we're going to be solving equations with the variable on both sides, but using a more visual way to look at what that solution actually means. And then we're going to actually go to solving with the balance, a visual balance that we're going to use with Sketchpad. And we're going to end with solving systems of equations, where we're going to use multiple representations, so simulation, graphing, tables, lots of different ways. So this is where we're going to go today in the presentation. So we're going to start with the solving by undoing. So before we actually get into the activity, I wanted to send one more quick poll out to everyone, because undoing involves students knowing how to use order of operations. So the question I've just sent out, and again, let me read it for my Mac users. It says, by the time students reach pre-algebra or algebra, they can evaluate expressions using order of operations fairly efficiently. So you're to respond either true for most, true for some, true for a few, or not true. So I'll just give you a couple minutes to and I am noticing that people are saying they're losing sound, and I think it has to do with my polls, so I'm going to stop talking. Andres, is my sound going out?
I do think it goes out briefly whenever you open a poll, and maybe when you close it.
All right, so I won't talk. Okay, the end of the poll question 4 is to evaluate expressions using order of operations fairly efficiently. So my Mac users, my questions get cut off for some reason. All right, I'm going to close this. And then let's share the results. I'm trying not to talk while I'm doing this. So it looks like an interesting, the first 2. So most students, okay, not a lot, not every student, but most students are pretty efficient. It is something that we focus on in elementary and middle school, so hopefully by the time they get to pre-algebra, algebra, you may have to do a little reteaching, but for the most part, they're coming to you with a fairly good understanding, and let's hide this, of order of operations. And so to start solving equations by undoing makes sense because conceptually that's something students understand, and we're just going to take their knowledge that they have and build on that and add on a new idea. So we're going to use their understanding of order of operations to help them understand solving equations, because solving equations is simply undoing what they did to get the equation. So now, and I changed my screen resolution, and it has now, I just want to move this up so I can see things. There we go. All right, so what I'm using here is a pre-made sketch. So I want to talk about that real quick. You guys are all going to get the sketch and the worksheet that goes with this. And I'm not going to be doing every page in the sketch, but this is a multi-page document. And you're going to all get copies of this. And this is a pre-made where I am simply interacting with it. I didn't have to do any creation. The idea is that we can get right into the mathematics but still using Sketchpad. So this is all done for me, and I am simply choosing to use my arrow to choose things to do. It's already pre-made. So we're going to start with a problem. So here's a problem that a student, if they know their order of operations, would probably be able to evaluate if you gave them a value for x. And so what this model does is use algebras basically, and it gives you a specific value for x, and so a student could plug in a specific value that's given and evaluate this to see if it equal to 2. So they'd use their order of operations, which in this case is they would add 3 first to whatever value we plugged in, and then divide by 4, and would it equal 2? If it did, then they found the value. So sort of a guess and check idea. So we're going to use this visual representation of order of operations and actually work through. So current value of x, if I add 3, so I'm going to push a button that's going to take the current value of x and add 3, and so this is now the current value, which is about 6. I could change the input and it would change my current value, and so I'm doing the order of operations, add 3. The next step is to divide by 4, so I'm going to take this current value right here after adding 3 and divide it by 4. And now here is my end result. Well, what do we want the end result to be? We wanted it to be 2. Is it currently 2? No. So this value of x is not the correct value. So what value of x is going to make this end result here be 2? Well, it would help if I could actually see where that end result is going. What I'm using here are custom tools that come with this sketch. So again, you don't have to create any of this. This is all part of the sketch, and the worksheets tell you how to use all the custom tools, so we're not going to go through that now because you're going to get that at the end or when you download the zip file. So I'm simply going to get this tool called the indicator, and that lets me put a line on the end result of this problem, and I want the end result to be at 2, so I'm going to move my x until that line gets to 2, and that will give me an approximate solution for x. So it looks like it's about 5. So that's doing order of operations. Well, what if the students were given this and they didn't have these nice little algebras, but we're going to use them to help us visualize undoing to solve an equation? Well, what's the end result here? The end result is 2. So an undoing to solve for an equation is you start with the end result. So the end result is 2, so that's where we're going to start. So if you think about what we teach kids when we're doing problem solving, one of the methods we teach them to solve problems is to work backwards. So solving equations by undoing is a working backwards problem solving strategy. We take the end result of 2 and reverse everything that happened, use our inverse operations. So let's get a bar that represents our end result 2. And notice it lines up with the last operation that we did, so it's a nice kind of symmetrical lining up here. So what was the last thing? We got 2. What happened right before we ended up with 2? Well, we divided by 4. Remember our last operation. So now we're going to undo that. So what do you do if we know our operations? The inverse of dividing by 4 is to multiply by 4. So we're going to take our end result working backwards and use the undoing method and undo division by multiplying. So we're going to multiply by 4. And so again, you'll notice the nice symmetry here. After I undo division by multiplying, I end up back with the operation I did right before that, which was to add 3. So we're lined up here. The bars are very symmetrical. It's creating this nice symmetrical visual for the students to explain how undoing is simply reversing everything that happened. So now what's the step before this? Well, I added 3. How do you undo adding? What's the inverse operation? That's to subtract. So we subtract 3 and we end up here, which is the resulting x value, which we were looking for. So this is giving them a visual of how undoing to solve an equation works. You're simply taking your order of operations and using inverse properties to solve them. So you can start using this model, and you'll notice as we go through, there's another problem here, and we can use the same idea, and notice there is no little push buttons here. Now the students have to actually, if you're going to use this with students at their computer, they can actually follow the steps on how to use the tools. Or if you're doing this as a classroom demonstration, how would you undo this operation? Well, let's go to our custom tools. Again, these are part of the sketch, and we want to start with the end result, which is the value of 1. So I'm going to create a bar that represents my value of 1. So now I have my end result value of 1. Well, this end result, remember we've got that symmetry that we're supposed to be creating. This end result does not match this end result. So I need to move my y to get that end result to match as best I can. And it looks pretty close there because I'm trying to make that symmetric. We're undoing, so we should have bars that are symmetrically balancing out, I guess is what you want to do. So what happened before I had 1? Well, I subtracted 5, correct? And so I want to add 5. So we're going to take our current value, and again I'm going to get one of these tools, and undo the operation that happened right before, which was to subtract. So to undo that, I'm going to add, and I'm going to show where I want the bar to be, and take my current value of 1 and add 5. And so if I did it right, I should now have a bar that lines up with the step right before that, undo, the inverse operation. So what happened at this step? Well, I multiplied by 2, so how do I undo that, or what property is the inverse? Well, I'm going to divide. So again, I'm going to get my custom tool, and I'm going to choose the division, and I want to create a bar starting here, and I'm using the current value, which is 1 plus 5, and this time I am dividing by a 2. And again, I am lined up exactly with where the current value of y is, which is 3. So what we're showing here is visually showing how the end result, by undoing, we get to the value of y, which in this case is 3. That should work if I plug it in. So if I could do this in my head. 2 times 3 is 6. 6 minus 5 is 1, and it worked. So again, just a visual to help them understand what this undoing property is doing. And so then there's another example, and then what I would suggest, and I'm looking at my time and I want to make sure I get to my last activity, which I ran out of time yesterday. So I'm going to do something very quickly, and I'm going to be using a Sketchpad 5 tool. So this is not a tool that is in Sketchpad 4, but if you have Sketchpad 5, it's a tool that I would use here, because one of the things when you are working with students with models such as this, you don't want them just doing the model. You also want them to be writing down the symbolic representation or the mathematics of what they're doing as well. So I'm going to use this marker tool to just use a marker, and this is in Sketchpad 5. If you didn't have Sketchpad 5, you could still do the same thing but use your text tool instead, just by typing in, creating a text box and typing. But I'm going to use the marker tool just because I want to demonstrate the marker tool, and it's a little bit easier. So we're going to look right here at this problem, and I want to make sure I didn't miss my poll. Hold on. I actually want to go back to this other one. I'm on the wrong problem. I want everyone to look at the problem that is currently up there. And if this were your students, we're going to basically practice doing this without having the model first worked out. We're going to actually just start with the undoing. So if you were a student, what would be the first operation based on this problem? So 2 times a plus 5 minus 1, all divided by 3, equals 1. What would be the first operation that they would have to undo? So I'm going to send out this poll and we'll just see. And again, my Mac users, I apologize. It's definitely going to disappear. But it's basically asking you what is the first operation, so I'll give you a couple more minutes to look at the problem, that should be undone in this particular problem. So I'm going to send out the poll and we'll see, because this is what you're trying to get your students to do. And so for my Mac users, it's just asking you which is the first, and it just has the same equation there at the end. And we'll just give it a couple minutes. And I'm going to close this because it seems to be a resounding answer here. So I apologize if you didn't get to respond, but everyone was choosing correct. Multiplying by 3 would be the first operation that you would use. So we're going to hide that. So if this were something I was doing with my students, either as a class demonstration or on their own, maybe on their own paper, I'd have them actually write out the steps that happened in the order so that they then knew how to work backwards. So for example, what happened in this problem? First we added 5. Then we multiplied by 2, and I'm just following order of operations. Then we subtracted 1. And then we took that answer and divided by 3. So here's all the operations that happened in the order that we would have done them in a normal order of operations problem. And we ended up with a 1. So our end result, and we'll just circle our end result, was 1. So for students, writing that down helps them figure out, how do I work backwards? How do I undo my inverse operations? So we're going to do that now with our model. We're going to start with this value of 1, my end result. So I'm going to get my value, and I'm going to start with the value of 1. And then I'm looking at what I wrote down. What's the next step? Well, I want to undo dividing by 3, which you all said was to multiply by 3. So I'm going to go get my tool here, and I'm going to take my current value of 1 and multiply by 3. And so here is this step that undoes the dividing by 3. Well, what happened right before dividing by 3? We subtracted 1. How do you undo subtracting by 1? You are going to add 1. So let's get our adding tool here. And we're going to take our current value and we're going to add, did I do that wrong? I think I did it wrong. Hold on. No, I didn't. Sorry. Let me start over here. Oh, there we go. So there we go. And then what happened right before that? I multiplied by 2. The inverse of that, undoing multiplying by 2, is dividing by 2. So we're going to take our division tool and we're going to take our current value and divide by 2. And then the last thing we did, or really the first thing that we did if we were to solve this problem, was to add 5. So to undo adding 5, we're going to do the inverse, which is to subtract. And so now I have my current value and subtracting 5. And I end up with an answer, whoops, over here, and it looks like it's -3. And so then I could then plug it in and test, did that answer work? And I have all the steps that I did to undo this operation. So for some students, this really helps. Undoing to solve equations is a very helpful way for them to understand what's happening when they're trying to solve for x or solve for a variable, solve an equation, because it makes sense. They understand order of operations and you're just reversing order of operations. It may be a little more time consuming, and that's okay because we're eventually going to get them to a point where they want to be a little more efficient, but right now this really makes conceptual sense. And for some students, I know when I was using this in my classroom, I had students who could never solve an equation, but once we started doing it this way, They could solve any equation I threw. It didn't matter how complex it looked, how many different operations were going on. They could do it because they were just keeping their order of operations in mind. And they'd write down the steps and just work backwards. So it's just a suggestion. Again, this webinar is simply giving you some ideas of how you could help students solve equations in maybe different ways than you've thought of before. I'm going to move on to the, yeah.
So one question that came up, which you can use as a segue into the next section, is just how is this approach different from balancing an equation?
It's really not, in my opinion. It's really not. It's really the way that we're having them write things down. It's a perfect lead-in to solving equations by balancing. It is exactly balancing, but if you think about how we kind of force students into writing down solving equations by balancing, we force them to write the +1 on both sides of the equation and the dividing by 2 on both sides. This is just asking them to undo one operation, so they only see what's happening one time. But you're right, it really is exactly the same, and so if you start doing this and then go into solving by balancing, it's almost the students are like, oh, well, we've already been doing that. That's my take.
And one other question that came up is, with the last example you just did, someone asked, what do we say to a student who now asks, where's the symmetry? I think the symmetry is not visible because you didn't go through the process originally.
Correct.
Starting with A and building it up to the final answer. And so that's why you're seeing the undoing process here in the absence of the doing process.
Right. The idea behind all of these models is to eventually get the kids to a point where they don't need the models anymore. The models are there as a way to help students understand why we're doing things, why things work. And so when you start off, you're definitely going to want to start off with the symmetry so they understand that the undoing is just keeping things balanced. But eventually, so this is, and you could stay on these types of activities for a long time, but eventually you want them to get to a point where they actually don't need the model anymore. So here we didn't do the step through the order of operations. We simply wrote it down here instead of using the bars to represent it. We simply wrote down the operations versus doing it with the bars. And so that's why they don't see the symmetry. Because eventually you want to get them to the point where they don't even need the model. So at this point, maybe they don't want the model anymore. The models become almost cumbersome, which is what you want. You want them to just be able to look at this and say, oh, I need to subtract 5, and then I need to multiply by 3, so that they're getting to the point where the model is no longer needed. All of these models are just to help students understand and reach that symbolic manipulation that we're trying to get them to.
Great, thank you.
All right, so now we're going to move into approximating solutions, and I am going to just preface this. I am building this from scratch. I'm following the directions on the worksheet type of thing. If you were to do this with your students, if you were in a lab, it's not a bad thing to have them maybe do it by scratch because it's teaching them some neat Sketchpad skills. And I'm showing you by scratch just to give you some Sketchpad skills that maybe you didn't know or see. But if you were to do this, say, as a class demonstration, the work that I'm doing to get to the actual model, I would probably have done beforehand so that my students are just seeing the end result of the model. And this model is approximating, where we're not going to get exact solutions necessarily, but we're doing it more to give the students an understanding of what does it mean to solve for equation. This is dealing with variables on both sides. So the kind of equation I'm speaking about is something like this, where we have an equation where it's got the x on both sides. And so what does that actually mean? What are we really looking for when we say solve for x? Well, we're looking for, this is really two expressions, and we're looking for the value of x, where x creates the same answer on both sides. That's what we're doing. And so this model is simply a visual of that, where we're going to focus on the two expressions on each side and solve them simultaneously and visualize them simultaneously. So again, what I'm about to do, I'm really kind of doing for your benefit just to show you some Sketchpad skills. But if you were to do with your students, I might actually have already got the model done so that we're not taking the time. So what I'm going to do is basically make two number lines. So we're going to think about input and output. So x is our input value, our domain, and y, the answer, the end result, is our output. So I'm going to create a number line for each, an input number line and an output number line. So to do that, I'm simply getting my graph and defining a coordinate system. I'm going to hide my grid because I really just want the number line. And I'm going to do a couple things here. And again, this is all on the worksheet, so you'll get the directions on this. But I'm going to define the distance between these 2 points first. So I'm going to measure that distance. And I am going to put a point somewhere down below where I want my other number line to be, my other horizontal number line. And I am now going to define this number line to have the same unit, I forget what I'm trying to say, same scale as the one above it by choosing this point and the distance represented up here to create a new number line, basically. So it's going to create a new number line on here. So again, I'm going to go back and hide my grid. And I want to hide the axes as well, so I'm just going to choose them and hide. And there's actually 2, so I got to hide the other one. And I don't need these points anymore. These points were simply used to help me create my number lines, and so I no longer need to see them, so I'm going to just make them invisible. So now I have these 2 number lines, and because the second one was created using the first one as its kind of control, whatever I do to the first one, the second one will follow suit. So I have these 2 number lines, and I'm going to use the first one as my input. So I'm going to get a point and place it on the number line, and this is now going to be my X value. So I'm simply double-clicking the label and changing it to represent my X, my input. And I'm going to measure this value, current value of X, and I believe, Andres, correct me if I'm wrong, this particular, this is under the measuring thing, but I believe this is only Sketchpad 5 for measure value of the point. Am I correct?
That's correct. And Sketchpad 5 has implicit number lines, so it will, when you have an object like a point on a line, it has a value in that implicit number line. In Sketchpad 4, you would have to measure the abscissa.
The abscissa. So you still can do the same thing, it's just a little different in Sketchpad 5. So Sketchpad 4, you'd move this. But we're going to do this, and this simply gives me the value, and let's make that label say X as well. So this is the current value of the X, and notice it's dynamic as I move X on the number line. And did the screen just disappear? Oh, there we go. And so now what I want to do is plot the output. So what do I really have? Well, I have 2 expressions here, and if I plug X in, I'm going to get two values for my output because there's 2 different expressions here. So I'm going to basically treat them as 2 separate equations, I guess. So I'm going to get my calculator, and again, you can do this in Sketchpad 4 and Sketchpad 5, and I am going to calculate the value, the output value, using each equation. So 3, and I'm going to use this dynamic measurement of X, and I'm going to click. And so now I have basically the left side of my equation with the current value for the output, and as I change X, it plugs in. Okay, is my screen going in and out, Andres? Can you tell?
It seems fine to me.
Okay, because my screen, it keeps blinking, so I'm just curious. I'm hoping nobody's having issues with the screen. So let me do the same thing for the other side of the equation. So I'm going to go, again, get the calculator, and I'm simply going to type this equation in, 2 times the value of X. And so now what I'm doing is I am comparing both sides of that original equation. And what is the solution? Well, the solution is when I input a value of X and I get the same output value. So we could just move this till we find the same value, which I happen to know the answer, so I'm going right to it. So that's one way to find it, but I also want to see, what does this look like? What does it look like when I have the correct value for X that solves this equation? So we're going to take these 2 outputs and actually plot them down here on my other axis. So I'm going to click this. Oops, no, I got to get my tool. This is a custom tool again. And I'm going to choose this and the axis I want to put it on, and there is the output point there. And we're going to make this a special color so it's different from the others. And so now I actually visually see the output of this side of the equation. And let's do the same thing for the other side. And let's change this color as well. Oh, what's a pretty color? Let's make it blue. And then let's connect these with segments. That makes it even more apparent for what we're looking for here. And maybe even change this color to green. So all of this stuff that I'm doing right here, this is, if I were to do this model with the students, I would probably have done this ahead of time so that when I'm working with the students, I am actually just moving the model around and the model's already done. Though it's not bad to have your students. So now look at the model. What are we looking for? We're looking for when the output and the input, and let's move this up here when the outputs match. So when our input ends up matching. So right there. So physically, those points are now on top of each other. That's what this physically looks like. Solving this equation with the x on both sides, it means that we've input a value where the end result is the same on both sides, and this is what it physically looks like. And now that you have this model, you can actually change this equation to anything that you want. So I could change this to be let's just make it pretty easy here. Oops. Let's make it 3 times x plus 10, plus 10 minus 5 equals 2 times x plus 6. I can make it be anything. And so once I do that, I then need to change these. And it's very easy to change a calculation once you have it. You simply double-click it and you get back your calculator. And we're simply going to change this equation to match what's on the screen now. And I think I have, minus 5. And what it will automatically do is change the equation here and also change the output where it is on the bottom here. So now they don't line up anymore. So let's change this side as well. And this was 2 times x plus 6. And so now what's the solution to this set of equations? And so again, we're going to move our model until we have them lined up. And it looks like it's about 13, a little bit off. So you could use this model just to visually demonstrate what's actually happening when we're solving equations where you have variables on both sides. So my question to you now is, would this work? Would this particular model work if you had nonlinear equations in one variable? So it does have to be one variable because notice we have an input and an output. So one variable. We're not working with 2 here. So I'm going to just send a quick question out to everybody. Do you think the model will work if we had nonlinear equations in one variable? And while you're doing that, I'm going to actually Okay, it looks like we have most people voting, so I am going to close and share. And we're going to hide. So most of you are saying yes, so let's just do a real quick check on that. And okay, there we go. So I've got this new equation here, which for some reason, there we go. So again, I need to change my 2 equations simply by double clicking, and so now I've got, and it might be easier just to start right on over here, so x squared plus 5x plus 3. That's my first side, and notice it's off my screen, so let's get it a little bit closer there. And then let's change this other side, and the other side is 2x plus 13. And so let's see if this model is going to work. And we should have, okay, so as we move, there is an answer, x at about 5. And then as we keep moving up, it hits again, and there's a different answer at x equals 2. So it does work, and actually that was -5, not 5. It does work for nonlinear equations as well. So again, this is just a visual representation of what does it actually mean to solve when you have variable on both sides. What does it actually mean? What does it look like? It's just a way to help students understand what we're looking for, and if you were to use this, I personally would probably have this set up and where you can just manipulate the model already. But if you have students in a lab who like to learn some Sketchpad things, that's another option as well. They could start it themselves. So I'm going to move on to our next model unless Andre says we have questions.
Karen?
Oh, hi, Scott.
Can I jump in for a second?
Absolutely.
I just want to observe that that I really like the way you did this, because by dragging the x, we get to see a very different picture of what it means to have two solutions to a quadratic equation.
Right.
And we see how each side of the equation is behaving, and how at some point they come together to form another solution. So I just wanted to observe how nice that how nicely this represents it, very differently but nicely.
I agree. I didn't create you. I mean, you're probably the one who created this. Who knows? All right. So Andre, is there any questions before I move on?
No.
Is Andre still there? Okay. So the next model is the one that we typically associate when we're solving equations. It's the one that we tend to do with students. I remember standing up in front of my classroom with my hands looking like a balance beam and that type of thing. I'm sure you've all done it. So this is a model that is using the balance idea, the solving where you have equal, doing the same thing on both sides of the equation. So very much like undoing, and I'm going to hopefully kind of bring up that connection here as well. So this particular model I wanted to explain because it does involve negatives. So anything that's positive is a weight, which means it's pushing down on the scale and making it heavier. The negatives are balloons, meaning they're lifting up. So by this time, you've worked with students, and this is why doing order of operations and inverse operations is important, because hopefully by now they have the understanding that inverse operations or inverses, the -5, +5, are going to create 0, and that has no weight and can be removed from the side of an equation. So they get several examples of equations, and again, when you're working with students, we're always trying to eventually get them to not have to use the model. So always try to have your students on paper, on the sketch, however you want to do it, writing down what they see and what they're doing as they manipulate the model. So in this particular one, again, I'm going to use the marker tool. Actually, I think I'm going to start with my text tool. First thing I would have them do is, what is the equation that they see right now? So x minus 5 equals 2. So if they've been doing undoing, they probably look at this and go, well, I already know the answer to that. It's very much in my head. But we're just going to demonstrate the model right now. So what would they do? They would try to isolate x. Well, how do you isolate x if you have a -5? You need to get rid of it, so you need to do the inverse operation, which is the opposite of -5 is +5, or the inverse of negative is positive. So we're going to, whoops, need my arrow tool, add a +5, but notice my balance is no longer balanced, which means I have to do the same thing on both sides. What have I actually done? Well, we simply added 5 to both sides. Well, what happens in the model, or if they're understanding inverse operations, this right here creates a 0. And that 0 doesn't weigh anything, so we can take it away from the balance, and therefore it has had no effect. We took away nothing, basically. But on this side, we now have x by itself, so we are left with our x. And on this side, we are left with a value of 7. So it is very much taking that idea of undoing and simply writing down both sides, keeping the idea of balancing. Again, you're trying to get students past that, so hopefully maybe they are going to go, wow, the balancing, that's a lot of extra work. Now I'm not going to do every one here. I'm just going to keep showing you that there's lots of different examples as you move along. And one of the things I wanted to point out is there are negatives both of the variables and of the numbers. So if we tried this one right here, what equation do we have? We have x minus 1 equals negative 3x minus 5. So really by now, if you have worked with students in undoing first and they really have that understanding of inverse operations, these problems are relatively I don't want to say easy, but they're going to have a better understanding of them because they're just looking at this as inverse operations. So what am I trying to do? I'm trying to get this x by itself, basically. But I've got some x's over here. How do I get rid of the negative x's? Well, I know the inverse to cancel them out is to get those positives in there. So I'm going to add in some positives. But it's not balanced now, so I really need to be adding in the same the same on this side to maintain that balance. And what did I just do? I might want to write it down. I added 3 positives, but I needed to add the same thing on this side. And what happened on this side of the equation? Well, I just created 3 zeros. And so I can take these 3 zeros away because I know that they don't weigh anything. But what am I left with? I'm left with my 4x's now, and my negative 5 and my negative 1. And so now I don't have my x's alone anymore. So how do I need to get rid of the 1. So you continue to work with the model by adding the 1 to both sides. And we're going to get rid of our 0 here. And again, you'd want your students writing down what they're doing with the model, but also writing it symbolically so that they're making that actual connection. So what did I just do? I added the inverse 1 to both sides, and so now what's left in my end result is 4x and a negative 4. Well, how am I going to represent division in my model? Well, at this point, maybe the students say, well, we already know we're going to divide by 4. Here's what they're left with, by the way, 4x. Because remember, these models are to help them understand what's happening, but eventually you want them to get to a point where they need the model. So at this point they say, well, I know I'm going to divide, I'm going to do the inverse operation and divide by 4. Maybe they won't need the model at this point. But what if they do need the model? Well, what does dividing by 4 actually look like on the model? That means you are taking what you have and splitting it into 4 equal groups. Well, how do you take something like this that I can't make into 4 equal groups? Well, is there something I could do to replace this? Well, what's this really worth? This is worth negative 4, so I could replace this with 4 negative balloons. And as long as I keep my equation balanced, I now have 4 negative balloons, but now I can split these into 4 equal groups, and each one of these groups is worth a negative 1. So in my model, each x is a negative 1. In my symbol manipulation, if I actually show the inverse operation, I end up with a solution of negative 1. So the model is there to help them understand the manipulation that we're doing with the symbols. And eventually, and you'll see as we continue through the sketch, eventually it gets to a point where they don't want them using the model anymore because the model is simply a tool to help them get to that understanding.
Karen?
Yes, Scott.
Could you show on that last sketch the actual last step?
This one? Which one? This one?
Yes. If you were to draw a selection rectangle, exactly.
Yeah, I was going to take away all these.
All those guys, because each of those rows is equivalent to the other.
Right, absolutely.
And then you show the final solution, which is very nice.
Exactly. So again, the idea behind all of these models is a way to show students what's happening visually, because some students need that, and to help them understand the manipulation that we're doing with the symbols, but eventually the models are no longer needed, and so you are going to end up at the point where they should be able to solve without the model. The model is a tool to help them get there. It may take some kids a very quick time to get there, and it may take kids not very long. So the last thing that I wanted to show was because eventually they've solved equations, but now we want them solving systems of equations. And so I wanted to, yes?
I might have missed it on the last model, but did you, I think it's important just to note that the balloons are actually pulling up on each side of the scale, and that's the way negatives are represented.
Yeah, I said that at the beginning.
I apologize. I was answering somebody's question.
That's
Go
okay.
on. Thanks.
All right, so the last one I wanted to show you is hikers, and this is basically just, it's an example of solving system of equations, but using Sketchpad to work through the multiple representations. And I speak of this, and unfortunately my little thing, because I've been working with the Common Core a lot in some of the work I'm doing, and one of the things in the Common Core standards is it's really important for students to be able to use graphing tables and find different approximations on and determine what answer is more important. So sometimes an estimate's good and sometimes an exact answer, and which form of solving is going to give me the answer that I need. And so helping students use multiple representations to get to solutions of systems of equations is one way to help them understand when it's good to use a table, when it's good to use an equation, when a graph's good enough. So this problem is an application problem of a system, and so I wanted you all to think very quickly about, I don't think I'm going to do that. I'm not going to send my poll question. So here's the problem. We've got two girls, and they're starting at two different locations. They're going at two different speeds, and the question is, when are they going to meet, because they're on this trailhead, this path, and how far from the trailhead, the beginning of the path, are they going to be when they do meet? So this is a typical, you probably recognize this as the train problem. Two trains leave the station, when do they cross? But students have a hard time with this because what we ask them to do is write the equations and solve to get the answer. And a lot of times they don't even understand what's going on. So one way to help students to understand and even make an estimate is to do simulations. And you can use Sketchpad to help you do that. And all I've done is a very simple simulation. And it's got a line segment representing the path, and so I just pulled in some pictures. It's really easy with Sketchpad 5 now to just pull pictures in. So this is the trailhead, the beginning of the path, and this is the lake, and they're walking towards each other. And we're just going to use a little bit of animation here and kind of keep track of when they meet. Boom. Everyone get the answer? And I know I think it might be going a little slow. So I can slow it down. I have a time slider. And so what I want everybody to kind of look at, and actually I don't think I have this poll question on here on this one. I don't, darn. So if we look at the simulation, so we're just doing a simulation where it's kind of keeping track. So what are we looking for? What's the solution to this problem? Well, the question is, when will they meet and where on the trailhead? So what time and how far from the trailhead will they be? So in this very simple simulation, it looks like we're getting an estimate about 3.5 hours they're going to meet. And if we just look at this segment that represents the 12 miles, well, it looks like it's a little less than half. So I already have an idea of what the answer is before I even start trying to write the equation or trying to solve it, just by doing a simulation. And so Sketchpad's a great way to do simulations and get approximations of answers. And is that enough? Maybe I want the exact answer, so this estimation is not enough. So now how am I going to get a more precise answer? Well, what would be the next thing that we could do? Well, we have some information about Edna and Maria, so we could create a table of values and plot some points. So here is Edna, and I changed my resolution so things are not fitting where I want them to. So here's the table, and we've got time and we've got each distance. And so what do we know about Edna? We know Edna was going 1.5 miles per hour, and her distance from the trailhead was increasing. So the expression that represents Edna would be she started at 0 at the trailhead and adding 1.5. So where would she be after an hour? And I can simply type in my value here. So she's at 1.5. Well, let's look at Maria. Well, where was Maria compared to the trailhead? And I want everyone to think real quick, and if you need to go back to the problem we will. Here's the problem again, because I'm going to ask you guys to choose the equation that represents Maria's distance at any time. So I'm sending this poll real quick. And so Maria is 12 miles away at the lake, and she is going 2 miles per hour. What would be some equations? Thinking of your students, there may be more than one answer up there. Which one would be a possible solution for Maria? Oh, you know what? I think I did not make this poll. This was supposed to be where you could select more than one, because there actually is more than one answer here, I believe. And I'm going to close it. Okay, this is my fault. I forgot to choose the correct solution where you could choose more than one answer, because there actually is more than one possible answer here. She started at 12, so those of you who chose that fourth one, 12 minus 2t, that is a correct solution. But the first one as well is also correct, and I unfortunately didn't choose the right poll choice where you could pick multiple answers. And what I was trying to show was that students sometimes, the way they're thinking, they may give you the answer in different forms, and that's okay because it means the same thing. Her start value was 12, and her distance is decreasing because she's getting closer to the trailhead, so her slope or her rate of change is negative. So either 12 minus 2t or negative 2t plus 12 were the possible choices. So very good. So let's hide that. So let's go back to our table, and I'm going to click my quick fill it in. So here's the table of values, and so one other way to look and find solutions to problems is to look at the table of values. And so what do we already know from the simulation? We know that they're meeting at around 3.5 hours, which is somewhere between 3 and 4, and they're going to be less than halfway. Well, does this table, this particular table, give us that any more information than what we already know? Well, not really. It doesn't give us exactly what we need, but if we look, it does verify that what we thought the answer is true, because in the table, if we look at this particular table area, their values are switching here, and it is somewhere between 4.5 and 6 they're going to pass, which is less than halfway. So it's verifying our simulation. It's still not giving us an exact, so how could we get an even more precise answer? Well, we could plot these points. So if I plot the points, I now have what looks like, here's Maria and here is Edna. And where is the solution lying? Well, it's where they're crossing right here, and it looks like we've got a constant rate of change, which makes sense because they were going constant speed. So now I'm going to move on. So the graph's maybe going to get me a better answer if I could actually see the lines. So I'm going to go to my next thing. So here's this graph. And very much like I did on the approximating, there's a point on this axis that represents time. And then we created a expression that represents Edna. So for Edna, we've got 1.5 times time, because that was Edna's expression. And then we've got for Maria, we've got 0 times, or 12 minus 2 times time, the equation that you all just came up with. So each one, that's their output value, very much like what we did in that other activity. And so now I have their points. If you look, I don't know where Maria went. There she is. So now I have points that represent these values, and it would be nice if I could actually see the path, because I'm looking for this point where they're actually meeting, and I can see right here that's lining up. So if I trace it and actually create my lines, my graph.
Karen?
Yes?
When you speak and move things at the same time, it causes problems.
Oh, that's right. Sorry. So the graph now I have a graph of where they're moving, and I see, do I have a more precise answer? Well, I'm getting pretty darn precise here. I have 3.45 at time 3.4, which was pretty close to what we estimated, but now it's a little more precise. And then 5.1 looks like the point where they meet. So this graph gives me a more precise answer. Is there a way to get an exact answer? Well, that's where then the equation comes into play. So we actually now plot their equations. So you'll notice this is the plot, or the plot of the function Edna equals 1.5 times x, and this is the plot of Maria's function. And then we can calculate the exact, and now with Sketchpad 5, I can actually choose my two functions and construct that intersection point, which is right there. And now I can measure the coordinates of that point. Whoa, and they're very big. And that is the, let's make that significantly smaller. There we go. That's the exact point. Well, then how could I then maybe make the connection between these two equations, maybe have them actually solve the equation symbolically using some of the methods that we've talked about. So this is just showing you how helping students get answers in lots of different ways and giving them reasons for when's an estimate good enough, or when do I need a precise answer, and what type of solution gives me a more precise answer. The graph is more precise than the table. The equation is exact. So you're helping students to make the decision of when do I need to solve the equation, or when is an estimate enough, or when can I just kind of get the idea from the table or from the graph. So I'm pretty much done with what I wanted to show you, and the whole idea today was to simply give you some ideas and suggestions for things you could be doing with your students. You are going to get a link to the zip file of these sketches that I've used today and the worksheets that go with them. So that's probably going to be up by Thursday. And also this webinar has been recorded, and you can also play that back as well. So we have a couple minutes left, so I wanted to spend the last part just thanking Scott and Andres for being online and answering questions, thanking all of you for joining us, and then answering any questions that maybe need to be answered before we call this an evening. So are there any questions, Andres, that I should answer?
Well, I'm not seeing any questions. I know Scott had a comment that he was going to make earlier about undoing versus the balancing model. So Scott, did you want to talk about that? Or?
Well, I just wanted to observe that the balancing model, in the balancing model, you've really got all the different pieces in sort of you've done whatever simplification is to be done. If there was a multiplication, then of 3 times x, then you put 3 x's there.
Right.
So there's no question at that point of undoing that multiplication, but of taking sort of what amount to the simplified form, which is what's sitting on your balance pans, and moving things around using the equivalences of a -1 and a +1 make 0, a negative x and a positive x make 0. You can add the same thing to both sides. You can subtract the same thing to both sides. So it's using those operations on the simplified form in the balance. And one of the beautiful things about this, I think, is that doing that operation, which is very different from undoing things in the systematic way that we did in the undoing activity, but they give exactly the same results. Isn't that beautiful about the way mathematics works?
It is. It is.
While we're on this page, we should also clarify that the final answer there should be x equals negative.
Oh, sorry, you're right. Hey, I can't think and write at the same time. Come on.
Actually, it wasn't me, but there was at least 3 participants that informed me that the answer was wrong. So thanks for letting us know.
I told them that you were just trying to keep us all on our toes and make
there
sure
you go. That's right. It was totally deliberate. I did want to answer a question I just saw scroll across the screen. The files that come with it that you're going to get, you actually are not going to get them in an email. You're going to get a link, and I can tell you the link right now, keypress.com/webinars. When you go to the archived recording of this, the document download is right with the archived recording. So they're on the same page. So no, it's not, the email is not linked, it's not sent to you in an email. It's actually on our website, and you're just given the link to the website. So the recording and the archived files are all in one spot. You will get an email again for those of you who joined us late. We are starting with this webinar sending out certificates of attendance. So basically you'll get a certificate in the mail that says you've attended 1 hour of professional development training on Sketchpad and algebra. So those of you who can use something like that for your continuing education units or whatever it is your district maybe accepts, you're going to be getting those. For those of you who've attended past webinars, we are not going back and sending any for those. This is simply starting with the one this week. So future ones, they will all have certificates, just so you know, future things. Any other questions? If not, we're going to say good night. Thank you very much. I know for some of you it's kind of late, and we appreciate you joining us. And thanks again, Andres and Scott, for hanging in there and answering all those questions. I appreciate your help. And thanks, everyone, for catching my mistakes and helping with the webinar and keeping things going. We appreciate your comments. When you leave, there is a very quick survey, and we do take those comments very seriously, so if you have suggestions or questions, please make sure that you put them in the survey, and we will respond to you.
All right, I want to thank all of the participants who are thanking us for the webinar. I want to thank Karen for the presentation. We will stay on for a couple more minutes so that if anybody still has some questions they'd like to ask us, we'll continue to answer those up until about 5:05, maybe 5. And then,
or 8:05 in some worlds.
Right. And anyway, thanks for attending the webinar, and this will officially be the end, but go ahead and continue to ask questions if you have any, and we hope